Now let's do a slightly more complicated, though very similar example to the process. This question says, estimate delta H combustion for the combustion of butanol and compare it to the value obtained using delta HF values. Remember, our bond dissociation energy examples are estimates. And delta HF values are what we can think of as our correct values. So for the combustion process, well, first of all, if this were on your exam, you would have butanol and what it is, and you'd have a balanced reaction. So butanol, it turns out, but means 4 carbons, AN means connected by single bonds, OL means there's an alcohol. So if we were to draw it as a skeletal structure, it would be 1, 2, 3, 4 OH group. So that is butanol, and its formula with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 would be C4H10O plus O2 goes to carbon dioxide plus H2O. These two are gases because this is combustion. Our butanol would be a liquid. Yes. And we said this works best for gases, but let's see how it works for this. Our process from the previous slide says 1, draw Lewis structures, and that's so that we can see all of the bonds. Actually, before we do step 1, I always forget this step. Let's balance the reaction. Let's put a 1 in front of the butanol. Then that means there must be 4 carbon dioxides and 5 H2O gas or water vapors. From there, I have 8 and 5 is 13 oxygens on the product side. I have 1 oxygen, so I need 12 more. There has to be a 6 right there. And just a reminder, we have 2 pages, and this is partially for me. We have 2 pages to do this problem. Now, that should be balanced. Now let's draw Lewis structures. We'll start with our butanol. I have 1, 2, 3, 4 carbons. Then an alcohol group. Now, Lewis structures have all pairs of electrons, so I will draw my pairs of electrons on my oxygen. And then I will fill in all my carbon-hydrogen single bonds until each carbon has 4 bonds. And you could do this right on the skeletal structure if you want. That'd be fine. And I do get 10 hydrogens. Oxygens, Lewis structure O2 has a double bond in it. And so let's write plus 6 goes to 4 carbon dioxides. Carbon dioxide has 2 double bonds in it. And we'll put 4 there. And then plus 5 H2Os. And I'll draw my H2O vertically there so it fits in, because I always seem to be running out of space on this side. Now I have Lewis structures for everything. My next step is to do, and we did that step in red on the last slide, is to find the bond dissociation energies. What I'm going to do is add a slight wrinkle here, is I'm going to total up my bonds first. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon-hydrogen single bonds. I have 1, 2, 3 carbon-carbon single bonds. I have 1 carbon-oxygen and 1 oxygen-hydrogen. And then I also have 6 double bonds between 2 oxygen atoms. Over on the other side, I actually have 4 times 2 C double bond O, and I'm going to put a little asterisk here, and I'll explain why in a minute. And then I actually have, let's call this 5 times 2 times oxygen hydrogen single bond. Okay, so those are all the bonds. Now I have energies for those, so I go to my list here, and I see that these are the single bond dissociation energies, and right below that is a table of double bonds and single, double, and triple bonds of certain atoms. And let's see, there we go. For CO2, the C double bond O bond is 803 kilojoules per mole. So this is going to be 4 times 2 times 803 minus, and then this is going to be 5 times 2 times oxygen hydrogen is 467, and that's minus as well. Here, now onto the positive ones. 6 times oxygen, oxygen double bond. So oxygen, oxygen, 498. And that's positive. And now I've got, let's sort of keep this semi-organized. Carbon, hydrogen is 416. Carbon, carbon is 356. And what you'll find as you move from book to book in general chemistry is that they're all relatively close regardless of the book, but they're not all exactly the same. That's why in the previous one I had 243 instead of 242. They're estimates, and these estimates vary depending upon the source, but they're all very close, and they're all improving over time, as you might imagine. 1 times carbon, oxygen, 336. Yep, that's what it says. And 1 times oxygen, hydrogen is going to be 467. And another approach simply says to take this off and take this down to 9, but we'll leave it how it is for now. So add everything up, get some big numbers here. So 9 times 416 plus 3 times 356 plus 336 plus 467 plus 6 times 498, 8,603. So it says delta H reaction equals 8603 kilojoules per mole. Minus, or let's say, I like to do plus, then do my minus numbers over here. Call me crazy. 8 times 803 minus plus 10 times 467 minus. I get minus 11,094 kilojoules per mole. I think I did most of it on this one page here, for better or worse. All right, and so now delta H reaction is going to be 8603 minus 11,094. I get minus 2,491 kilojoules per mole. Good that it's negative because this is combustion, and combustion is an exothermic process. Thumbs up. Now let's see how we do compared to the other method of doing it, which is going to be using delta HF values, and we'll return to this pen. C4H10O plus 6O2 gas goes to 4CO2 gas plus 5H2O gas. Now we're going to look up the delta HF values. And I'm not sure if C4H10O is on my list, but I definitely looked it up somewhere so I could do this problem. And it is minus 328. I must have Googled it. These are kilojoules per mole. Oxygen is 0. Carbon dioxide is minus 393.5. Let me double check that on my list. Yep. And let's write that down. H2O, gas. H2O, gas, minus 241.8. So we're going to get 4, 5, and my delta H reaction, which is now these numbers minus this negative number. I know, it's confusing. It's needlessly so, some might say, but your job is to figure out what makes sense to you and how to do this. So this is going to be 4 times 393.5 negative plus 5 times 241.8 negative minus a minus, so plus 328. And I get minus 2,455 kilojoules per mole. That's compared to minus 2,491, which on the face of it, you're off by a little less than 40 kilojoules per mole. But if we do a percent error using the delta HF value, or the delta HF derived value as our correct number, minus 2,491, which is our experimental, or it's our different technique, minus 2455 over minus 2455. Oh, stay on the page there. Times 100%. We're going to get a relatively small percent error. Minus 2491 plus, so there's two minuses there. 2491 minus plus 2455 divided by 2455 minus times 100%. 1.5% error, which is pretty darn good considering that we knew nothing about the molecules, nothing about the molecule other than what kind of bonds it had, and one of the starting points was a liquid. This is a completely general and powerful procedure for estimating delta H of reactions, specifically for gas phase materials. However, it can be applied to other situations as well.